Now that we looked at the history of Roebling and the education and his life experience, let's move on to his three major works, beginning with the Niagara River Bridge, 821-foot span, completed in 1855. In 1850, we talked about the Britannia Bridge in the UK by Stevenson. This was a railway bridge, and it was intended to have suspenders, hence the awkward tall towers. The Niagara River Bridge at 821 feet needed those suspenders, and it also needed a deep deck, just like Britannia had. Here, the span is much larger, therefore the truss and the cables both are needed, whereas again in the Britannia, only the deep deck was needed. The Niagara River Bridge essentially established Roebling's reputation as a master builder of suspension bridges. Roebling had a rival, just like Stevenson and Brunel were rivals, but they were rivals but friends. Roebling was not friends with his rival, and that rival was Charles Ellet. Charles Ellet actually was awarded this project for the Niagara River Bridge, but before the project starts, Ellet gets fired for reasons unrelated to the project. While Roebling was building his Niagara River Bridge, the Wheeling Bridge over the Ohio River, another suspension bridge that was built by Charles Ellet, collapses in a windstorm. This gets Roebling nervous, and he asks Trenton to send over more wire rope. So if we look at images of the Niagara River Bridge, we see that he's attached the cables to the bottom of the deck down to the ground. So not a very elegant solution, but a safe one, and the Niagara River Bridge was safe against wind. During the Civil War, there was a concern that this bridge would be destroyed. Therefore, Union soldiers guarded this bridge. It was considered an important bridge. Now let's move on to the Cincinati Bridge. This was completed between the time period of 1856 and 1866. It was interrupted by the Civil War. This spans over the Ohio River and slightly over 1,000 feet in span. So we went from about 500 feet order of magnitude in the last lecture over in the UK with Telford, Stevenson, and Brunel, and now we're up to in the order of magnitude of 1,000 feet. And at the time that it was completed, it was the longest spanning bridge in the world. We can see with the Cincinati Bridge the style that Roebling is developing. It's really the precursor, it's the prototype to the Brooklyn Bridge. Initially, in 1846, Roebling had proposed two spans on the order of about 788 feet each. He revised that span to be one span after the successful completion of the Niagara River Bridge. So again, when completed, it was the longest spanning bridge in the world. Since its completion, the Cincinati Bridge has been renamed after the engineer. It is now called the John A. Roebling Bridge. So with this background of Roebling, his life, his experiences, we can examine now his greatest masterpiece, the Brooklyn Bridge. So the rest of the lecture will be dedicated to this masterpiece, the Brooklyn Bridge. So how did John Roebling's vision of the Brooklyn Bridge come about? It actually happened in 1852. That's when he got the idea for the Brooklyn Bridge. He was on a ferry boat, stranded on the East River, which is right behind me, because chunks of clogged ice blocked the channel. He began dreaming and thinking about a bridge crossing this East River, but it was a very large span, and it would have to be much longer than the Cincinati Bridge. He wrote letters to the New York press, and eventually, in 1865, a bridge company was born. Now we're going to examine the Brooklyn Bridge from the scientific, social, and symbolic aspects. So from the scientific aspect, we're going to look at some terminology related to loads and the parts of a suspension bridge, and look at the form that it has for gravity and wind. From the social point of view, there's a lot of politics to talk about, and economy, of course, is closely related to both politics and the social context. And finally, from the symbolic point of view, we know it to be one of the greatest icons in the world. We're going to look at its opening and how the artists respond to this bridge. A rendering drawn by one of John Roebling's assistants, Wilhelm Hildenbrand, shows what the vision of John Roebling was for the Brooklyn Bridge. So with this rendering, we can see that indeed his vision, his original idea, is what was constructed, or very similar to it. In the preface to a report by John Roebling to the New York Bridge Company in 1867, he wrote, quote, The contemplated work, when constructed in accordance with my designs, will not only be the greatest bridge in existence, but it will be the great engineering work of this continent and of the age. Its most conspicuous features, the great towers, will serve as landmarks to the adjoining cities, and they will be entitled to be ranked as national monuments. This isn't exactly modest, but actually history has shown it to be true. The towers of the Brooklyn Bridge actually, when completed, look like skyscrapers in the context of the Brooklyn and Manhattan skyline, and I'll come back and show you that later. From the scientific aspect of the study, today I'm going to focus on some terminology, for example, the loads. In engineering, we call dead load something that's a permanent load in the structure. It's essentially the self-weight of the structure. So in the case of the bridge, it's the load of the deck, for example, will be something to be considered the dead load of that bridge. Then we have live load. Live load in the case of a bridge is the traffic load, the weight of the vehicles, the weight of the pedestrians. It's a transient load, something that's movable. That's what we refer to as live load. We also have wind forces on any structure, buildings, as well as bridges. So we'll talk about a little bit about those wind forces and what part of the suspension bridge, the Brooklyn Bridge in particular, is dealing with those wind forces. Let me explain to you a little bit about the different parts of the bridge and the terminology used to describe the different parts. We have the deck, and the deck of the bridge is supported by the suspenders. The suspenders are the vertical elements of a suspension bridge, and these elements essentially pick up the load of the deck truss, which carries the dead load and the live load. And the suspenders then, in turn, transfer their loads to the cables. The cables are the draped cable that goes from the top of one tower to the top of the other, and then back anchored against the anchorages of these suspension bridges. The cables transfer the load to the anchors, but also to the towers, and the towers bring the load down to the foundation. In the case of the Brooklyn Bridge, we have stays. Stays are the diagonal elements. They're like the suspenders. The suspenders are vertical, the stays are diagonal, and they essentially control the deformations that could be induced by the dynamic effects of wind. So Roebling learned this lesson through the Wheeling Bridge collapse, and he applied those cables tying down the Niagara River Bridge from the bottom of the deck down to the ground, a solution that wasn't very elegant. In the case of the Cincinati Bridge and also the Brooklyn Bridge, he includes these stays, these diagonal elements, again, to control the possible deformations due to wind through the lessons that he was learning of the bridges that were having trouble due to wind-induced vibrations. Some other terminology that you've heard of before, but I'm going to apply it in the context of structural engineering, is compression and tension. So compression is when an element is being squeezed together, and tension is when the element is being pulled apart. So when we look at a structure, we have to be able to identify which parts are in tension and which parts are in compression, because that is the foundation of how one goes about designing those elements. So I have a question for you. If we look at this Brooklyn Bridge, look at the tower, the cables. The cables, again, are the elements that go from tower to tower. They drape from tower to tower. And look at the suspenders, those vertical elements carrying the load from the deck to the cable. Which of those elements are in tension and which of those elements are in compression? The answer to the question of which elements are in tension and which elements are in compression is option A. It shows that the tower is in compression, the cable is in tension, and the suspenders are in tension. So through your homework assignments that you will be doing, you will be able to understand this more fully and also be able to calculate the actual forces and stresses that these elements are carrying. To continue the story of the Brooklyn Bridge, I need to introduce to you Washington Roebling. Washington Roebling is one of John Roebling's sons, and he received his degree in civil engineering from the Rensselaer Polytechnic Institute, known as RPI. It's a great school for engineering and one of the first engineering schools in the United States. He was a colonel in the Civil War, and he worked with his father on the Cincinati Bridge. Towards the end of that Cincinati Bridge project, Washington Roebling, actually took over most of that project because John Roebling was busy preparing for the Brooklyn Bridge. Eventually, Washington Roebling took over the construction of the Brooklyn Bridge as well. In 1869, while surveying the East River, determining where exactly to place this Brooklyn Bridge, John Roebling was standing on the piles of a dock. As the ferry docked and pushed back those piles, his toes got crushed. He refused medical attention. He believed in the healing power of water and tried his own methods, but unfortunately they didn't work, and 2 weeks later, John Roebling died of lockjaw. Fortunately, his son, Washington Roebling, was educated in civil engineering, and he takes over the project. Washington Roebling was a great builder and a great engineer, and well prepared to handle what we would call, say, the technical aspects of bridge construction. But he was not prepared for the social part, meaning the politics and corruption that would follow.